In this video, we want to look at an easy way for multiplying and dividing complex numbers if they are in either polar form or exponential form. All right, so here's what we want to start out with. So starting out with saying that you've got one complex number, and this is going to equal r sub 1 times cosine theta sub 1 plus I times sine of that same theta sub 1. Right? And then if we have a second complex number with a different radius and a different angle measure, what's going to happen if I multiply or divide these guys? Now, while we're here, let's go ahead and also say that we could express this in exponential form as r sub 1 e raised to the I theta sub 1. And this second one could be r sub 2 e raised to the I times theta sub 2. So when we do multiplication, it's going to be the product of those r's. And if we're doing the polar form, it's going to be cosine of theta sub 1 plus theta sub 2 plus I times sine of the sum of those angle measures. Now, in terms of the exponential form, this would be r sub 1, r sub 2, e raised to the I times, and you would add these angle measures up there. Okay, so that's multiplication. It really does simplify some things. So if you know your r and you know the angle, it's very, very quick and easy. Now, if I'm doing division, and of course, we're assuming here that z sub 2 is not 0 because just like with real numbers, you don't divide by 0 in complex numbers. So if you have division, you will be dividing those magnitudes, those absolute values, times cosine of, and then we'll do theta sub 1 minus theta sub 2 plus I times sine of theta sub 1 minus theta sub 2. And in exponential form, that's going to be the quotient of r1 over r2 times e to the I theta 1 minus theta 2. So we want to look at some problems here where we're just told to multiply and divide, and we're not going to make things super complicated. We could, but we're not going to, all right? So if, for example, I tell you that z sub 1 is 6, I'm going to use the shorthand here, CIS of 70 degrees, and z sub 2 is 9, CIS 45 degrees. Let's look at the product and let's look at the quotient. So the product says that we would do 6 times 9, so do that product on the outside. And then for the product, we're just going to be adding these angle measures. So it would be CIS 70 degrees plus 45 degrees. In other words, 54. And let me expand out the CIS. Fine, whatever. So it's going to be cosine of 70 plus 45 is 115 degrees plus I times sine of 115 degrees. And that would be the product of these two numbers. Now, if we've got this in polar form, it really doesn't take much for us to see what would this be in our exponential form, because the product of the two r's is still going to be 54, and instead of writing cosine 115 plus I sine of 115, well, we would definitely have to make a conversion on that. But you know what? In this example, we're not going to do that. So let's pretend I'm not doing that. So we just want to leave it in polar form for this one, and we're going to do polar form for the quotient here as well. So by doing doing the quotient, it's going to be taking R1 over R2 times, and now we're going to do the difference here, so 70 minus 45 degrees. And yes, it does matter which one's in the numerator, which one's in the denominator, because that's then going to determine the order for your subtraction. So remember, with multiplication, the order is not going to matter. With division, just like with subtraction, order does matter. All right, so this is equal to 2/3. 70 minus 45 is 25 degrees, plus I times sine of 25 degrees. Okay, fairly straightforward, I hope. All right, let's look at another example, another pair of complex numbers. This time without degrees, we're going to be using radians. So if I say Z1 is 6e to the I times pi over 3, and Z2 is equal to 4e to the I times pi over 2. So we're going to have these for our two complex numbers, and let's find the product. So the product would be just taking 6 times 4, the product of those two R values, R1 and R2, and it's going to be e to the I, and then inside here we have to add these thetas, so pi over 3 plus pi over 2. All right, so we have 24e to the I, and again, if you need to write the work over here, do that. Get the common denominator, which is 6, so this becomes 2 pi over 6 plus 3 pi over 6. So it means up here we have 5 pi over 6. There's your product. If you wanted to write this in polar form, I mean, that'd be pretty simple, because this would just be 24 cosine of 5 pi over 6 plus I times sine of 5 pi over 6. And once you've got the exponential form, getting polar form, it's like no big deal whatsoever. Now, what we could do if we were asked to do it is that I could evaluate each of cosine and sine, multiply times 24, and come up with what the two pieces are, what the real part and the imaginary part are. I don't know that I really care to do that. I mean, I can. So if we were to keep on going with this, cosine of 5 pi over 6 is negative square root of 3 over 2. And 5 pi over 6 for sine is going to give us 1/2. So this is going to be 1/2 I. Multiplying gives me negative 12 square roots of 3 plus 12i. And we could use the graphing calculator to check this product to see if it does, in fact, give me that. But I'll leave that to you for an exercise. Now the next part is to do division. So Z1 over Z2 starts off by doing R1, 6 over R2, 4. And then e to the I, and this is now where you do the subtraction. So that's going to be pi over 3 minus pi over 2. So 6 over 4 reduces to 3/2. E to the I. Now, we can kind of cheat a little bit and use what we've already done. So I know I need to subtract these, and I need a common denominator. But if you look up here, we already know what they look like with common denominators, except this time instead of having plus, we'll have minus. So 2 over 6 minus 3 over 6 gives me negative pi over 6. Now, if you don't like that, remember how this guy is going to be periodic. And so negative pi over 6 is in the same location as 11 pi over 6. So either one of these answers would be perfectly acceptable for the exponential form. All right, so coming up next, we're going to be looking at using de Moivre's theorem, which is actually quite cool. especially since we have this exponential form that we're working with. So with that in mind, I hope you come back for more.